So my name is Brian Weston, and I'm a PhD student at the University of California, Davis, and I'm doing my PhD research at the Lawrence Livermore National Lab for the ALA 3D team. And my advisor at Livermore is Robert Norgalia, and my PhD thesis advisor is Jean-Pierre Delplanque. The focus of my talk is going to be on the preconditioning of a high-order, fully implicit, reconstructed discontinuous Galerkin method for the Navier-Stokes equations. So our work is funded for applications in additive manufacturing, where we want to come up with a laser melting simulation. And so this multi-physics problem has numerous challenges. First, our simulations are going to require laser-induced powder melting, where we have the formation and solidification of liquid melt pools. And so we're going to have to deal with very complex interfacial physics, such as surface tension, Marangoni convection, wetting, and evaporation of the steel. Secondly, there's actually argon gas trapped between these steel particles, and so we're going to have to track the multi-material interfaces between the liquid, gas, and solid phases, where there are over 1,000-to-1 density ratios between the solid-fluid interfaces. Since we can't ignore rapid density variations due to evaporation and condensation of the steel, we have to treat all of the materials in a fully compressible framework, which adds to the complexity of the problem. So currently, we're just right now focusing on the melting and solidification phase transition of the fluid and solid. So to give an outline of my talk, I'll first go over the governing equations of our problem, and then I'll talk about our high-order spatial discretization scheme. Then I'll move on to our fully implicit time discretization, which is based upon a Newton-Krylov framework for handling tightly coupled physics. Then I'll get to the focus of my talk, which is really on designing a preconditioner for this problem, where right now we're using direct solves preconditioned GMRes. And then I'll show results for my preconditioner on kind of 3 different problems of increasing complexity. And lastly, I'll just conclude and show our future direction. So first, Robert and his colleagues have used an explicit reconstructed discontinuous Galerkin method for aerodynamic applications focusing on high-speed shock dynamics. And so now at Livermore, we're focused on adapting this high-order method for tightly coupled physics applications, such as in phase change in our laser melting problem, where there are very strong nonlinearities and tight coupling between your momentum and energy equations. Previous members of our team have tried to use both explicit and operator splitting approaches, and both methods were ineffective because of the severely restricted time step limits due to stability. So this kind of motivates our transition now to a fully implicit Newton-based approach. So the equations that we solve are the compressible Navier-Stokes equations, written here in generic form. U is your solution vector in conservation form. The F is your hyperbolic fluxes. D is your diffusion operator, and S are your source terms. Right now in our source terms we have gravity, but eventually we'll be adding in surface tension and a laser source heating term. We're dealing with a classic Newtonian fluid here, and we have several equations of state for closure of our system. And right now we're able to handle homogeneous equilibrium phase change with a temperature formulation to track the different phases. And so since we actually have a distinct phase transition temperature between the solid and the liquid, we have a mapping to internal energy where the latent heat is kind of the jump in internal energy from the solid to the liquid. So this is a visualization of one of our problems where we have a solid, basically solid steel here in a liquid melt pool, and you can see we have a very thin interface between the two. And the way we're treating our solid right now is we're using a very simple viscosity-based strength model. And so we essentially say our solid is a liquid, but with a very high viscosity. Right now we're using a factor of 1,000. And all of the material in between is kind of in a mushy transitional region. And so what this does by using this viscosity model is that we now have a 1,000-to-1 jump in viscosity in between a very small interface. Secondly, we have a variable coefficient diffusion operator now, because our viscosity is a strong function of temperature, which adds a very strong coupling between your energy and momentum equations. This type of nonlinearity in your parabolic operator is very difficult to treat numerically, and it poses a lot of challenges for the solvability of the underlying linear algebra. So since we're using a discontinuous Galerkin method, we're working in a broken Sobolev space, which allows for piecewise discontinuous polynomials between elements. And in any kind of standard Galerkin method, you have to introduce basis functions and test functions. For our basis functions, we're choosing Legendre polynomials. And kind of the name of the game is that you multiply by your test functions and you integrate by parts. And since we're actually using a fully implicit framework, we choose our test functions to be orthogonal to our basis functions, which is actually new in this work. And the coefficients that we actually solve for, the degrees of freedom that we solve for are these coefficients sitting in front of the basis functions. And technically, any Galerkin method is generalized as a method of mean weighted residuals. So I don't have time to talk about the reconstructed discontinuous Galerkin method, but if you're interested, you can see the details in our paper. I will, however, mention some of the brief advantages of our method over a classical DG method. So the first point is that our lowest order RDG scheme, P0, P1, is exactly a self-centered second order finite volume method. And so when we go to higher order, essentially, our method is a natural generalization of finite volume methods to higher order accuracy. Our reconstructed method is also, we're able to get kind of higher order for less cost. So to give you an example, in 3 dimensions here, in classical DG, you'd have to solve for, say, a fourth order accurate DG method, you'd have to solve for 20 degrees of freedom. And in our RDG P2, P3 scheme, which is also fourth order accurate, we only have to solve for 10 degrees of freedom. And this is particularly beneficial for the linear algebra because we now have smaller matrices that we need to approximate the inverse of. And by the way, the RDG P2, P3 scheme is kind of the common scheme that we use for the rest of the work. So we're using a modal-based method where we get higher order using linear elements in our code. So in 2D, we have quads, and in 3D, we use hexes. Everything is collocated, so our solution data management is simpler. And since our basis functions are hierarchical, this naturally facilitates P refinement and H refinement. The method was originally designed to allow for unstructured hybrid meshes, where you might want to mix quads and triangles. And the method is also very natural to implement if you want to implement, say, adaptive mesh refinement. Okay, so now that I've talked about our spatial discretization, I'll move on to our fully implicit time discretization. To discretize our time variable, we've implemented L-stable implicit schemes in the code. So we have like BDF2 and higher order implicit Runger-Cutter schemes up to fifth order accurate in time. And so once you kind of discretize in space and time, we're now left with this nonlinear residual equation. And this residual equation is of course a function of our degrees of freedom that we solve for every time step for BDF2 and every stage if we're using an implicit Runger-Cutter scheme. So to actually minimize our residual equation, we use a line search approach where we compute the descent direction along the lines of the gradient using an inexact Newton method within PETSI. And every nonlinear Newton step, we of course have a linear system to solve, and this is where our Jacobians kind of entered into the game. And so our Jacobians, of course, are the coefficients of the linearized system of equations that we now solve for. And just so you know, our Jacobian is a non-symmetric, indefinite matrix that's typically very ill-conditioned for our applications. To show an example, this is one of our phase change problems where we have a kind of a cold wall on the left and a hot wall on the right. And so we get like a solid frozen crust on the left and kind of a liquid melt pool over there. And this shows our nonlinear convergence output. So as you can see here, our Newton method converges within just a few iterations, 3 to 5 iterations here. And we're able to converge to very tight tolerances. So the mass and momentum converge to 10 to the minus 8, and the energy converges to 10 to the minus 5. For the linear solve for a non-symmetric system, we use the classic GMRes, where we're actually using the Jacobian free variant in PETSI with the finite difference approximation. And this is just to show you the eigenvalues of our unpreconditioned Jacobian, which kind of shows how our eigenvalues are all over the place. The condition number is on the order of 100 million and close to 1 billion, which shows how stiff our problems are. And previously, in our previous experience, we've tried operator splitting with Picard iterations, and it took thousands of iterations to converge for these applications, and sometimes it didn't even converge. And so now that I've kind of reviewed our Newton-Krylov framework, I'm going to move on to preconditioning, which is absolutely essential for the convergence of the GMRes. So we're actually using the right preconditioned form of the system, where hopefully where we now expose just J hat to GMRes, and hopefully our eigenvalues are hopefully clustered more like a ball. And the kind of two questions that we now have in preconditioning is, what linearized P matrix do you use, and what linear solver do you use to compute P inverse? So since our linear and nonlinear solvers are in PETSI, we decided we'd try the basic available preconditioners, the standard ones like ILU, block Jacobi, additive Schwartz. And so initially we picked our P matrix equal to Jacobian, and we tried ILU, and unfortunately it fails to converge. And then we tried other kind of block Jacobi variants like element block Jacobi, and again we have the same issue of no convergence. And we believe this is because of our matrices, because of how stiff they are, the eigenvalues are very sensitive to the important connections in the matrix. And when you use these kind of like canned preconditioners, they're agnostic in how they zero out connections. And so they zero out these important connections, and then GMRes struggles to converge. And so we were kind of stuck with, as an initial start, is the expensive but robust case, which is P equals J with LU factorization. The problem of this, of course, is very memory expensive. The LU matrix is much less sparse than your Jacobian matrix, so we wanted to kind of improve on this by coming up with ways of shrinking your P matrix by breaking the unimportant links. So this is our Jacobian structure. Our Jacobian, by the way, is a very sparse matrix, and it has a banded structure. The non-zero elements in our band correspond to the degrees of freedom from our higher order stencil. And there's kind of three different ways you can categorize our degrees of freedom. The first way is by equations. So you have degrees of freedom associated with, say, pressure, temperature, or velocity. Another way is categorizing them by your order of your degree of freedom. So you could have cell average quantities, your slopes, which are your first order derivatives, and then your curvatures, which are your second order derivatives. And kind of the last way is the proximity to your element. So if you're sitting on elements, the yellow element here, you could have degrees of freedom in that element. You could have degrees of freedom on the face neighbors or on the neighbors of neighbors. And so this is the structure of our kind of our band. And so there's a couple of different strategies that you can use to break these connections. So the first strategy is by what most people call operator splitting. So this would be like you're going to decouple your degrees of freedom associated with pressure from, say, temperature or velocity based on the equation. And this is routinely done in physics-based preconditioning, where you use knowledge of the physics to say, okay, I think pressure should be decoupled from temperature and velocity should be decoupled from temperature, and so you break your connections that way. Another strategy is by breaking it by the order of the degree of freedom. So this would be like you're going to decouple your cell average values from your slopes or your curvatures. And this is kind of routinely done in P multigrid, which is an algebraic multigrid, by the way. And so what they do there is your fine mesh would correspond to all of your orders, and your coarse mesh would refer to just your cell average quantities, and you'd coarse and refine between the two. And so kind of in the process of me learning about AMG, I realized that one of the important concepts is the strength of connection idea, which is central in defining your coarse grid points and your fine grid points. And I realized this is exactly what we needed for our problem, is we wanted an automatic way of detecting strong and weak connections. So I thought we'd just borrow this idea here, and we use kind of a similar thresholding approach. And so the way our algorithm works is that we build our Jacobian and we loop through the rows, and essentially we zero out quantities, off-diagonal quantities that are less than some user-defined epsilon times the diagonal value. And so by using this simple thresholding approach, we're able to zero out a lot of weak connections, and we're able to get some modest performance. Okay, and so to explain, our Jacobian is actually very expensive to compute. So what we do is we build it at the first time step, and then we reuse this frozen Jacobian for subsequent Newton iterations and subsequent time steps until we reach a Newton iteration where the number of Krylov iterations exceeds some user-defined value, typically 15 to 20, and then we rebuild that Jacobian and we freeze it again. To actually evaluate the Jacobian, we use coloring algorithms like smallest last within PETSI to reduce the number of residual evaluations to reevaluate the Jacobian. Okay, so now I'm going to kind of move on to our numerical results for the preconditioner, and we're going to show results for three different problems. Classic lid-driven cavity flow, which is popular in computational fluid dynamics, natural convection on a non-uniform mesh, and phase change. So and the last one is natural convection with melting and solidification. So in order of increasing level of complexity, nonlinearity, we first have lid-driven cavity flow, which is essentially passive advection, and your momentum and your mass and momentum equations are decoupled from your energy equations. But our condition numbers are still pretty high, on the order of 100,000. And this is because we're running with very large CFL numbers, and so our problem is still pretty stiff. The second problem is natural convection with gravity. And so now we have a weak coupling between your momentum and energy equation through a gravity source term. And this increases the condition number by up to about a factor of 1 million. And lastly, the most complex problem is phase change. And as I said before, there's a very strong coupling between your momentum and energy equations. And our condition numbers approach about 100 million and close to 1 billion. Okay, so for those of you that don't know, lid-driven cavity flow, you have these stone walls on the right, and you have a fluid in the middle, and your top wall is moving to the right. And so you develop these vortices and eddies. This is a velocity magnitude on the top, and that's temperature on the bottom. And we're actually running with a high Reynolds number case of 10,000 here. And we're using our P2P3 scheme with the BDF2 integrator. The second problem is natural convection. So all of the domain is kept at a constant temperature, but we oscillate the left wall here up and down to create this unsteady convection pattern. And we're running actually with a high Rayleigh number of 10 to the 6 here, and a very low Prandtl number of 0.1. The reason why we chose a low Prandtl number is because we're actually interested in modeling molten steel. And the melting and solidification problem has the same parameters, except we oscillate the left wall temperature below the freezing temperature, and so you get a crust on the left side. Okay, so before I show my results, we're going to compare, for efficiency, we're going to compare the P equals J baseline case versus our thresholding case that I developed, which we're denoting by P epsilon. Our figures of merit are going to be in kind of two separate categories. One's going to be memory expense, the other is going to be computational expense. In memory, we're going to look at the number of non-zeros in the Jacobian matrix, and we're also going to look at the number of non-zeros in the LU matrix. Right now, the L plus U matrix is really the bottleneck in our memory, but when we get rid of direct solves, then the bottleneck will be in the Jacobian. For runtime, we'll be looking at the number of residual evaluations required to converge a simulation, and also the nonlinear solver time. And there's kind of these other auxiliary metrics like colors, and the average GMRes iterations per Newton step, and the average Newton step, the number of Newton steps per time step. And the last two kind of correspond to how well your GMRes, basically how stiff the problem is and how well our Newton Crylab is working. Okay, so this on the top here, I'm varying the drop tolerance of our epsilon case. So on the left column, we're very aggressive with, we're picking 0.05, and on the right column, we go all the way out to 0, which is essentially just your Jacobian. And so on the left here, you see that when we're too aggressive, we get a similar results as ILU and block Jacobi. We don't even get convergence here because we're zeroing out important connections. And so what's in red here is essentially there's an optimal value of epsilon to minimize your runtime. So we're able, in this case, to reduce runtime by about 15%. And the memory, we're able to slash off about 50% of the Jacobian matrix, and only actually about 10% of the LU matrix, which shows that the LU is we really need to get rid of direct solves because it's not as scalable. And in this direction, as your epsilon gets larger, GMRes starts to struggle a little bit more, but it's still pretty close to 1, so, which means that we're only breaking the weak connections. And I forgot to mention that we're actually normalizing our results against the baseline P equals J case. So now I compare all three problems, and we're running with all with a CFL material number of about 4.5, and this is about acoustic CFL of on the order of a few hundred to 1,000. Lid-driven cavity flow is here, natural convection and phase change. In all cases, we slash out about 50% of the Jacobian matrix, about 14% of the LU matrix, roughly 15 to 20% in our CPU time, and GMRes doesn't even really change much because, again, we're only breaking weak connections here. So I want to conclude that we developed a high-order reconstructed discontinuous Galerkin method for the Navier-Stokes equations. This is built upon a fully implicit Newton Krylov framework to handle tightly coupled physics problems such as phase change. And we also developed a thresholding-based preconditioner with direct solves for low-speed compressible flow. Our future work is we're moving towards a block-based thresholding approach with direct solves on smaller subblocks. So right now the user picks a defined epsilon value and it's used throughout the entire Jacobian. But what we want to do is we want to pick a defined epsilon on each different physics block. So say pressure, we have to be more careful than say temperature. We also, instead of doing an LU factorization on the entire Jacobian, we want to do it on smaller physics subblocks. So we would solve pressure first, then temperature, then like say velocity. And we would actually move those off diagonals to the right-hand side and iterate in kind of a block Gauss-Seidel manner. Once we kind of get the direct solves working on these subblocks, we're going to move to iterative preconditioners like AMG precondition GMRes and GMRes GMRes. And lastly, since we only have physics on a very small region of the mesh, such as a laser spot, like a laser spot size, we don't want to build the Jacobian everywhere. So we want to come up with a way to locally build the Jacobian just around the physics. And that's what we'd like to also do. Thank you very much.